Hello, I am Christian Malaga, and this video will discuss the forced vibrations of damped single degree of freedom systems subjected to harmonic action. The key concepts discussed here are the characteristics of the transient and steady-state responses of forced oscillators and the dynamic amplification of their displacement response. To this end, we will examine the motion of this translating mass m representing a single degree of freedom system of stiffness k and a damping source characterized by a damping coefficient c, subjected to a harmonic force F. The equation of motion of this system is m times acceleration plus c times velocity plus k times displacement equal to the force in action, F. This equation can be normalized by dividing all its terms by the mass to arrive to this alternative expression in terms of the damping radius c and the natural circular frequency of the system, omega sub n. Since big F is a harmonic action, we assume it varies cosinusoidally with time, with a frequency omega and a constant amplitude. Furthermore, mass normalizing its amplitude will lead to small f naught, which will be equal to the original amplitude of the force, big F naught, divided by the mass m. Or, which is the same, to big F naught divided by k and multiplied by omega sub n squared. This last expression is obtained by recalling the definition of the natural circular frequency of the system as the square root of k over m. At this stage, it is important to distinguish between omega sub n, which is the natural circular frequency of the structure, and omega, which is the circular frequency of the force in action. The complete solution of this inhomogeneous second-order differential equation has two components. A particular component that defines the solution to this inhomogeneous ODE, and a complementary component that comes from the solution to this homogeneous equation. You should remember that this second equation was solved in a previous video. Let's start with the simpler case where no viscous damping is present in the system. In such a case, our equation of motion is reduced to this second-order differential equation. This second-order ODE defines the motion of an undamped single degree of freedom system. In order to solve it, we postulate a cosinusoidal displacement response with frequency omega and amplitude a naught. Differentiating it twice, we arrive to the acceleration, and substituting these into the above expression leads to this equation. We realize that the cosine terms can be factored out, and therefore a naught multiplied by minus omega squared plus omega n squared should be equal to small f naught. And isolating a naught will lead to this expression for the amplitude of our response. Substituting these into our ansatz leads to the particular solution whose terms are fully known. F naught is the mass normalized force amplitude. Omega sub n is the system's natural frequency. Omega is the frequency of the force in action, and t is the time variable. In order to arrive to the complete solution to the equation of motion of the undamped forced system, besides the particular solution we've just found, we need to also consider the complementary part which stems from setting the right-hand side of the equation of motion to zero. This can be recalled from last week's discussion, and it's equal to a1 cosine of omega nt plus a2 sine of omega nt. Therefore, the complete solution of the ODE will take this form. As before, the amplitudes a1 and a2 can be found by means of the initial conditions of velocity, v0, and displacement, u0. Looking at the complete solution to our equation of motion, we realize that the two parts previously mentioned have distinct oscillatory characteristics. We call the solution to the homogeneous part transient. This motion component depends on the initial conditions and oscillates at the frequency of the system, omega sub n. On the other hand, we call the solution to the particular part steady state. This motion component does not depend on the initial conditions and oscillates at the frequency of the force in action, omega. It is interesting to note that both components of the single degree of freedom forced motion emerge naturally from the solution to its equation of motion and play very distinct roles in the dynamic response of structures. Focusing on the steady-state component of the response, we can rearrange the terms and arrive to this expression in terms of the magnitude of the force, big F naught over k, multiplied by 1 over 1 minus the ratio of the frequencies squared. We realize that for a linear system that complies with Hooke's law, the ratio between the force and the stiffness is the static displacement, and we call this displacement U sub st. This static displacement represents the displacement that will be observed if the system is subjected to a static load of the same magnitude as the dynamic load, but without time variation. Let's focus on the equation for the steady-state displacement that we've just found and express it in a different way by defining an R factor, which is the inverse of 1 minus the square of the ratio between omega and omega sub n. This frequency ratio is sometimes called tuning ratio, and we are representing it here with the symbol beta. The R factor is the dynamic amplification factor and represents the ratio between the dynamic and the static displacements. In other words, R reflects how much larger the displacement response is as a result of the load being applied dynamically rather than statically. In our case, we are defining R in absolute terms, and therefore any eventual sign difference will be accommodated by changing the original cosine function to a sine function plus a phase phi. The variation of the dynamic amplification factor R as a function of the tuning ratio beta is shown in this graph on the left. Likewise, the phase difference as a function of the frequency ratio beta is represented in this figure on the right. Three types of responses can be identified in these graphs. A first case, when beta is lower than 1 and the response of the system is in phase with the external force. A second case, when beta is larger than 1 and the response is 180 degrees out of phase with the force in action. And a third case, when the frequency ratio is equal to 1, the response is unbounded and the system is said to be in resonance with the force in action. This video illustrates the physical meaning of what we have just discussed. It depicts the response of a single degree of freedom subjected to a support motion, a problem that we have discussed in previous lectures. This support motion is harmonic in nature. In the video, you will see a motor used to apply the harmonic motion. Recalling the equivalence between harmonic and circular motion, it's easy to see how this rotation can be resolved into a horizontal and vertical harmonic action. The single degree of freedom is formed by a mass attached to a spring, and you can assume very little damping. If the frequency of the action is lower than the mass spring system's frequency, we are below resonance, and the motion is in phase with the force in action. At resonance, the displacement is massively amplified and the response is out of phase with the action by 90 degrees. Above resonance, the displacements are low and 100 degrees out of phase with the force in action. As the tuning ratio increases, these displacements will tend to zero. Let's now look at damped forced vibrations. In such cases, the mass-normalized equation of motion of a mass spring dashpot system is this one. In order to solve it, we postulate a particular solution for the displacement response formed by a cosine and a sine term, both vibrating at omega. Differentiating it once with respect to time, we obtain the velocity, and differentiating it twice, we arrive to the acceleration. Substituting u dot, and u double dot into the equation of motion yields the following expression. The coefficients a3 and a4 adopt the following form and are expressed in terms of the circular frequencies omega and omega sub n and the damping ratio xi. As before, the complementary part of the solution can be taken from the solution to the homogeneous equation examined in a previous video, where omega d is the damped circular frequency of the system. Assembling the complete solution by adding the complementary and particular parts yields this expression. As before, we can distinguish a transient part that emerges from the complementary solution to the homogeneous equation, has a frequency of omega sub d, and depends on the initial conditions. In addition, we identify a steady-state part that corresponds to the particular solution to the inhomogeneous equation. It does not depend on the initial conditions and has the same frequency of the force in action. Importantly, the transient motion corresponds to the free vibration components that will die out due to damping. Hence, the more significant part is the steady-state solution. Turning now to the steady-state response, whose whole expression is presented here, we can recast it in more convenient terms by means of the following trigonometric identity, and we arrive to this expression. Here Umax is the amplitude of the displacement response and phi its phase. The amplitude Umax can be found by combining the squares of the A1 and A2 coefficients and taking the square root of that sum. Through some mathematical manipulation, we arrive to the following more compact expression for the displacement amplitude Umax. This is a function of the mass normalized force F0 divided by the square of the natural frequency omega sub n and multiplied by the inverse of the square root of 1 minus the square of the frequency ratio plus the square of 2 times xi times the frequency ratio. Recalling that the maximum static displacement is equal to the magnitude of the force big F over k, we can now define a dynamic amplification factor R as the ratio between the dynamic displacement amplitude Umax and the static displacement Ust, where beta, as mentioned before, is the tuning ratio between the forcing frequency omega and the natural circular frequency omega sub n. This dynamic amplification factor R is also called magnification factor or amplitude ratio and represents how much larger the displacement response is as a result of a load of a given magnitude applied harmonically rather than statically. This figure shows how the dynamic amplification factor R varies with the frequency ratio beta for different damping ratios xi. You can see how larger values of damping reduce further the displacement response over the whole range of frequencies. However, their effects are more pronounced in the central region of this plot. In general, 3 distinct response regimes can be distinguished from this graph. Let's look first at the left end, when beta is much lower than 1, meaning that the load is slow in comparison with the frequency of the structure. Here, the response is quasi-static and the dynamic amplification factor R is close to 1. Looking at the relative contribution of the inertial force, damping force, and stiffness force in the time domain for a beta equal to 0.2 presented on the right, you can appreciate that the inertial and damping forces are low due to the low levels of acceleration and velocity. As a result, almost all the forcing load is balanced by the force in the spring. If you were to operate over the dynamic response of such a system, you should consider first modifying its stiffness. As we move to larger values of beta, the amplitude of the motion becomes smaller and smaller, even reaching levels lower than the static displacement. Looking at the force history on the right, you can see that the inertial force dominates. When confronted with such a system, you will have better chances of modifying its force dynamic response by changing its mass. Finally, when the frequency ratio is closer to 1, the harmonic force in action is acting on the structure at about the same rate at which the structure prefers to vibrate. As a result, the structure offers little resistance to the motion and very large amplification factors are observed. The force history plot on the right for a beta of 1 and a damping ratio of 5% shows that all three force components are significant, but the inertial and stiffness forces are equal and wholly out of phase. Hence, they cancel each other, and the only resistance to the motion comes from the damping force. Under these conditions, you will have better chances of improving the dynamic response of the system by adding supplemental damper.